So in the previous video, we looked at the application of Newton's second law along a streamline for an ideal flow which we assume to be inviscid, that is without viscosity, incompressible, and steady. This led to the development of Bernoulli's equation, which tells us that the total pressure is constant along a streamline. Here we're going to look at the application of Bernoulli's equation, and in particular, the application we're going to look at is pitot tubes. Now, this device, a pitot tube, is found in many applications, but most notably it is found on aircraft. A pitot tube is a velocity measurement device. So in the left diagram here, we're showing the pitot tube, which is this L-shaped device. It's a hollow tube aligned with the free stream of the flow. So what we mean by free stream, this is the free stream right here. Free stream. Okay. So it's aligned with the free stream of the flow. And the fluid enters the pitot tube. And what it does, if we consider a streamline, it will stagnate over here. So here we say that it stagnates. And what we mean by stagnate is that the velocity goes to zero. So we're going to consider this location M. And so it has an elevation Zm. So the fluid enters the pitot tube, which is a hollow tube, and stagnates at the end of the pitot tube. At this location M, the local pressure is Pm. And that local pressure is measured in some way. So here I wrote a pressure measurement device, and that could be something like a MEMS sensor, a microelectromechanical system sensor, or a simple manometer. Okay? So right now we're assuming that we have some way of measuring that pressure at the stagnation point. Okay, so at M, we have an elevation Zm, we had a velocity of Vm, and we have a pressure of Pm. So let's apply Bernoulli's equation along this streamline, which enters the pitot tube. So along this streamline, we're going to have P infinity plus 1/2 rho V infinity squared plus rho G Z infinity, where Z infinity is this height over here. And this summation is constant along a streamline. And so at point 2 in the streamline, we will have Pm plus 1/2 rho Vm squared plus rho G Zm. So since the flow stagnates, we know that Vm is 0. And again, just to reiterate, this is a velocity measurement device which we seek to find out what this free stream velocity V infinity is. So this is very useful for an aircraft to know the wind speed, for example. Pm is known from the pressure measurement device, and Z infinity and Zm are also known. Okay, so we can solve for this. We find that V infinity is equal to 2 over rho multiplied by Pm minus P infinity minus rho G Z infinity minus Zm. So this is a way, if we have a way of measuring PM, such as a MEMS sensor, we can find our free stream velocity v infinity. Now, we can simplify this a bit. So typically pitot tubes are not very big, so I mean we could say that this is approximately equal to 0. However, this requires knowledge of the free stream pressure. So we can guess it, or we can assume it to be, standard conditions, at a certain elevation, or, standard conditions at sea level, etc. But we can avoid having to do this guesswork by employing a different device, which is called a pitot-static tube. Now, pitot-static tubes are very similar to pitot tubes, but what you have is you have an additional tube called a static tube. So again, what we seek to find is this free stream velocity v infinity. In the pitot tube, again, you have the same thing that happens where you have a streamline that goes into the hollow pitot tube and stagnates down here. And we're going to call this P1 for our purposes. Okay. Now, you have streamlines everywhere in the flow. So you're going to have another streamline up here. And this static tube is positioned normal or perpendicular to the flow. At this point up here, we're going to have something like still V infinity and P infinity. Right? There's nothing that has necessarily changed along this length. Okay. And down here, we're going to call whatever pressure that the second pressure measurement device measures as P2. Okay, and in this static tube, what we have is hydrostatic pressure, right? There is no dynamic pressure inside, so the pressure just increases with elevation there. Okay, so we have two pressure measurements now instead of just one. So let's write out what the pitot tube measures. So again, similarly to before, we're going to have So let's write out for the pitot tube, we're going to have P infinity plus 1/2 rho V infinity squared plus rho G Z infinity is equal to PM plus rho G ZM, where Vm is equal to 0, so we didn't include it here. And sorry, I'm going to rewrite these as P1 and Zm. Now let's express this as P1 minus P infinity. So this will be equal to 1/2 rho V infinity squared plus rho G Z infinity minus Zm. And we'll call this equation 1. And this is the equation stemming from the pitot tube. So now let's look at the static tube. So for the static tube, we just have P2 is equal to P infinity plus rho G Z infinity minus Zm. And this is just our hydrostatic equation. So we can write this as P2 minus P infinity is equal to rho G Z infinity minus Zm. And this will be our equation 2. So if we subtract, if we do 1 minus 2, what do we end up with? We have P1 minus P2 is equal to 1/2 rho V infinity squared. And so this allows us to solve for the free stream velocity, which we find to be 2 P1 minus P2 divided by the density of the fluid. So what we see here is that with a second pressure measurement device, we are able not only to eliminate the unknown free stream pressure, but we can also eliminate the elevation terms as well. And so this is a very typical application of Bernoulli's equation applied to a fluid flow problem.